So, what we will be doing in today's two lectures is we will be continuing on the notion of popularity that Prajakta has introduced. However, we will change the model of our problem. So, we are going to look at this notion in a different context, and the purpose of changing the model is to show you another model which is also very relevant and practical, as well as to illustrate that the notions that are used in one model do carry over in another model, and we will see the contrast again between the two things that we have seen. So, this topic will be popularity or popular matchings. So, we are still dealing with matchings in what is called as house allocation problem. So, as we did in the yesterday's class, we will be introducing the model. We will again talk about the notion of optimality. We will ask questions about does such an optimal matching exist? If it exists, how do you compute it? And like what we did for the stable matching problem, we will ask some questions about the strategic issues or the strategic aspects of this problem. Yeah. So, so the house allocation problem can be very well defined, can be defined in a similar manner. We have A1, A2, AN agents or applicants or people. There are also some houses, or we can also call them posts. So, we will call them in this, so that we distinguish these two models, we will call them A's and P's. So, we will call them P2 to up to Pk, some number of posts. Again, for the sake of exposition, we will say that each post or each house can be allotted to exactly one person. And like what we had earlier, an agent adds an edge to a post if that agent is interested, that applicant is interested in getting assigned to that post. So, we again have this underlying bipartite graph. The difference between these two models is that there we had agents as well as posts giving preferences over each other. Here one side of the bipartition is indifferent, that is it doesn't give any preferences. So, you can think of these houses, they do not care about who comes and resides into them, but the people really have preferences about, do I want a top floor house, do I want a second ground floor house, and so on. So, like what we had earlier, we will have applicants giving preferences. So, they will be again ranks. So, we will say, if I say A1 P1 has rank 1 and A1 P2 has rank 2, in our previous convention we were writing A1 P1 followed by P2, right. So, this is how we used to write. So, the same thing continues for the applicant side or the agent side. So, now we will just set up the notation and we will call them always applicants and posts. So, there are posts. However, I do not need to write any preferences for the posts because posts do not have preferences. So, there are only edges incident on them, and the edges are defined by the underlying bipartite graph. So, as soon as I write A1 P1, it assumes that P1 has an edge to A1 or that there is an edge A1 P1, right. So, this is the input to our problem, that is now you can think of it as a smaller input than what we had in the stable matching. We have some number of applicants, some number of posts, we have a preference ordering of every applicant over the post, and even to begin with we will allow ourselves to have incomplete lists. So, we will not force ourselves to have complete lists like we did earlier yesterday. So, these have incomplete lists, but we will not allow ties for the moment, that is we will not say that some applicant can rank both the edges A1 P1 as well as A2 P2, A1 P2 with rank 1, right. This is not allowed for now. So, there are no ties in preferences, but so there are no ties or what is called as strict lists. and we have been following this most of the time in our lectures. Yesterday there was an assignment in which you were asked something about ties, but for the part of the lectures we have been having strict lists. Okay. Yeah. So now we already know what is a matching in this setting. A matching is a subset of edges, no two of which share an endpoint. Now we will ask what is a notion of optimality in this setting. So this model is called as one-sided preference list model, as opposed to the two-sided preference list model where both the sides of the bipartition have a preference order, which is the stable marriage model. So now we ask what is optimality in this model, which is the one-sided preference list model. And since we have seen this notion of popularity, let's ask, can we use this notion of popularity in this setting of the one-sided preference list model, right? So let's make a concrete example and look at two matchings, right? We have already seen how to compare matchings with this notion of popularity in the two-sided model. Let's do this in the one-sided model. Okay, so instead of drawing the bipartite graph, maybe I'll write preferences. So this is the instance. So there are 3 applicants and 3 posts, and for now the preferences are complete, right? This need not be the case, and these are strict preferences. So let's take any 2 matchings, right? So any 2 matchings, so we will just take A1 P1, A2 P2 and A3 P3. On the other hand, let's take A1 P2, A2 P3 and A3 P1, right? So these are 3 matching, these are 2 matchings, both of them are perfect. Let us ask, how would you compare these 2 matchings? So let's name these matchings M and N, right? And how would you compare these matchings in the two-sided model? Yes. Yeah, so what we do is we write down the votes of all the participants, right? So we will do the same thing here, except that there you had written down the votes of A's as well as the B's. Here we are writing the votes only of the A's, right? So we will just write the votes of A1, A2, A3 for M and N. And we will see that A1 prefers the matching M over the matching N, so it gives its vote here. A2 prefers the matching M over the matching N, and A3 is the only one which prefers the matching N over M, right? So therefore, as we did in the earlier case, and because posts are indifferent, they don't really care about either being matched, unmatched, getting matched to any one of them. So they are indifferent between any of them, they do not participate in the voting. So we will say that M is more popular than N, like we did earlier. So we will just use the same notation, and we will say that a matching M is popular if there is no matching that is more popular than that matching. That is, when you look at this, look at a pairwise comparison, if you can find a matching which cannot be beaten by any other matching, we will call that matching a popular matching. So I'll again write down a matching M is popular if there does not exist another matching M prime such that M prime is more popular than M. Right. So note the similarity. I mean, stability was defined by the absence of a blocking pair. Similarly, popularity is defined by saying that if there does not exist a more popular matching, I will say that that matching is popular. Okay. So in the two-sided model where we have defined popularity, let's ask this question. Do popular matchings exist? That is, if I give you an instance of a stable matching problem with, let's say, incomplete lists but strict lists. So the question is, I am giving you a stable matching instance with all of the lists strict. They can be possibly incomplete. Then does a popular matching always exist? So please think about this question, and yeah, maybe you can raise your hands whoever thinks you know the answer. We would like to also ask the question in the house allocation, or I'll call that a one-sided preference list model. Which I have just defined. The same question, does a popular matching always exist? The first side is about the two-sided preference list model, the stable matching model. Yeah, so I just said that let everybody think about it. Yeah. So yeah, so what she says is that we proved in the class that a stable matching is a popular matching, and stable matchings are guaranteed to exist, and therefore we also have this guarantee that popular matchings always exist in the two-sided preference list model, that is the stable matching. So this answer is yes in this model. We as of now do not know the answer to this question, right? So let us do some more examples to understand the notion of popularity in the one-sided model. So now this. So this example is very similar to what we had earlier. There are 3 applicants and 3 posts. Now recall that I'm going back to the model of one-sided preferences. So only applicants have preferences over posts. So now this is the instance that I have, that is all the applicants have the same preference list. There are 3 applicants and 3 posts. So let's ask what matching is a popular matching here, right? So maybe just work on it, take 2 matchings and compare them and see whether there is one which is popular. Yeah, just hold. Okay. So order of what? Okay, so as of now we are not asking for an algorithm to compute a popular matching, while that is our intent. As of now I am just asking you however you want to compute a popular matching, pick some matching. Remember the way we did in the class yesterday morning? We said, okay, maybe I will try to match lot of people to their first choice and then get a stable matching, right? We failed in some of our attempts, but then we had to go for an algorithm. Similarly, by examining this or inspecting this instance, can you come up with a matching which doesn't seem to be, that is a matching that you cannot beat? We would like to get a systematic algorithm for it, but as of now that is not the question. Can you eyeball this instance and get a matching which cannot be beaten by any other matching? So did you try constructing a matching and it did not turn out to be popular? Okay. So let's wait for a moment. So anybody else behind in that row? Yeah. Did you attempt to construct any matching? Yeah. Okay. So let's consider her matching A1 P1, A2 P2, A3 P3. A1, A1 P2, A2 P1, A3. Okay, so let's do this comparison at least, right? So let's ask, amongst these two, is there one which is a candidate? Because I cannot say immediately by looking at two matchings whether one is popular. So that we have to understand. So let's first see whether one of the, if at least one of them does not work out, I mean one of them doesn't get beaten amongst the two, that is a candidate for being a popular matching. So let's see. So A1 votes for the matching P1, A2 votes for the matching uh, A2 votes for the matching P1. I'm sorry, I'm very sorry. This is M and this is N. So A1 votes for the matching M, A2 votes for the matching N, and A3 is indifferent, right? Because it doesn't care, right? So as of now, these two matchings, both of them do not seem to beat each other. For example, I cannot write this statement M more popular than N, neither can I write N more popular than M by this thing. Does this mean that they both are popular? So to check whether a matching was stable, we had to go at every pair and ask, are you a blocking pair? Are you an unstable pair? We would like to do this for every other matching. We would like to ask, is there any other matching that beats you? So for this matching, can you come up with another matching that beats, so for M, can you come up with another matching that beats M? You are saying no, right? You cannot come up with. Okay, so you cannot come up with, then you have to prove that this cannot be beaten. But if somebody shows us a witness matching, we are done, that we show that this is not popular. Okay. Yeah. Okay, this is your intuition, right? Okay. So she says that there cannot be any other matching that is more popular. A1, A1 P3. Okay, so I will use another color now. So you are trying to beat M, right? Okay. So you are matching A. Okay. Yeah. So A1 P3. Okay. A2 P1. and A3P2. Okay. So now let's look at the votes again, because once you change the matching, you may have to change, your votes will change, right. So therefore, let's ask between A1, between M and N, A1 votes for again the same matching, which is this M. Between these two matchings, A2 votes for this matching and A3 votes for again the matching N, right. So now we got another matching N which is more popular than M. So that intuition was not correct, that we cannot have any other matching that beats this. So maybe what this shows is that maybe N is a candidate. It shows that M is certainly not a candidate for being popular, because there is one matching which is more popular than this. Maybe N is a candidate. Do you think N can be a popular matching? Excellent. So there is an X maybe, which, so let's construct this because it's the first example we are seeing. So I will use another color, hopefully that is visible. X, where A1, A2, A3. So can you tell me what is your matching? A1, P2, A1, P2, A2, P3, A3, P1. Okay, so if you compare N and X, again these votes don't mean anything, these ticks and this thing. So we have to erase them and we have to start afresh. So A1 now prefers, A1 prefers this matching, the red matching. So we give the tick here, and A2 prefers, A2 is matched to P3. So A2 prefers this matching and A3 prefers again the red matching. So the matching, so what we had is N is more popular than M, but X is more popular than N. It would be very nice if X is more popular than M, then we possibly still have a candidate which is X, which is a popular matching. But let's do the comparison. So when we compare X and M, what happens? N is more popular, M. M is more popular than X, right? So we have M which is more popular than X, right? And what we see is that, in fact, if you take any matching, you can play this game of what we'll call as two promotions versus one demotion. What is a promotion? That is, when you look at between M and N, there are two people, A2 and A3, which are getting promoted or getting better partners or better posts at the cost of one getting demoted. And this game we can play with every matching in this instance. There is nothing specific about this matching. And in fact, one can ask, I mean, these are perfect matchings. Can you look at smaller matchings which are popular? That again is clearly not possible, because then you have left an applicant and post unmatched. Then you can get a more popular matching without even demoting anybody or getting somebody lower. So therefore, you can look at other perfect matchings in this. There are only 6 perfect matchings, and you can show that each of them gets beaten by some other matching, right. So what this shows is that in the one-sided preference list model, there exist simple examples, instances, such that no popular matching exists. Right. So there is a very simple example where there are no popular matchings. Now, just to contrast this with another example, let's say that I have many applicants A1 to AN, N can be a large number, and there is just one post P1, right. So there is exactly one post and everybody has an edge to that post, right. So There is a unique post, therefore there is nothing difficult about this instance. Now there are several matchings in this instance, in fact there are n matchings, each one of them has size 1 and each one of them just takes one of the AIs and matches it to P1, right. Now take any MI, so MI is equal to AI P1 and let us ask, is this matching popular? So let us take any other matching simply looks like MJ, because there is no point in taking the empty matching because that cannot beat this matching. So I just take MJ P1 and if I look at the vote table, then except for AI and AJ everybody is indifferent because they do not get matched in both of the matchings. AI votes for the matching MI, AJ votes for the matching MJ. And if you do this pairwise comparison between any two matchings, then it is the case that no matching can be beaten by any other matching, right. So there are in fact n matchings which are popular in this instance. And what I want to illustrate is that it has nothing to do with lot of applicants remaining unmatched versus everybody getting matched and so on, because in the previous example we had all matchings that matched all applicants, yet they were all not popular. Here we have all matchings matching just one applicant, yet all of them are popular, right. So it has nothing to do with number of applicants getting matched and so on, but it has inherently to do with the way the preferences are arranged, right. So what we learn from these two examples is that there can be instances where there are no popular matchings, there can be instances where there are many popular matchings, and when popular matchings exist, like it was said earlier, that it is a matching where no majority of applicants want to deviate, right. So when there is a popular matching, there cannot be a majority which votes for any other matching, because that is the way popular matchings have been defined. So therefore, while they need not exist, we would like to know if they exist, because when they exist they are a very appealing notion of optimality, because then majority of the people are with that matching and they do not want to deviate. Is this clear? Yes, yes, very much, yeah. Yeah, so the models are different. Her question is that if I put posts and then if I make the posts also give some preferences, some strict preferences, then of course there is a stable matching in that model, and that matching is popular in the setting where both applicants and posts vote, but that model is completely different. Is this fine? Any questions? Okay, so our next goal is to answer this question, how to compute popular matchings. Actually maybe even basic than that, does there exist a popular matching? This is the question we would like to answer, but we will answer it in an algorithmic, how to compute popular matchings. And we will answer the existence question also. Okay, so any suggestions about how do you think we can go about computing popular matchings if they exist? Yes. Okay, so there is no notion of a blocking pair now, but you seem to suggest that we should go in the order of preference, giving priority to, yeah. So, okay, so let's, okay, so there are these applicants. So just to make the example little interesting, I will have, okay, so maybe this is the example that is given to us. There are 6 posts and there are just 5 applicants, but that doesn't matter as we know. For example, I could have had many more posts in another example, but still that instance will not admit a popular matching if the initial preferences look like that, right? So, we seem to suggest that we should give priority to the top choice post, right? So therefore, let's ask what is every applicant's top choice post. So it should be, if we just draw this graph where every applicant just looks at its top choice post, right? So therefore, A1 adds an H to P1, A2 adds an H to P1, A3 adds an H to P2, A4 adds an H to P4, and A5 also adds an H to P4, right? So, if I draw this graph, if this graph happens to admit a matching where every applicant is matched, then we are very happy because that matching cannot be beaten by anything. Everybody gets its top choice, just like in the stable matching. If any applicant is, any A is matched to its top choice, it cannot participate in a blocking pair. Similarly, if all applicants get matched to their top choice, then there is no other matching that can beat it. But it will happen in, like in this example, that there are conflicts, that is there are A1 and A2 both of which want P1. Similarly, A4 and A5 both of which want P4. So should we fix a priori that maybe A1 gets P1, A4 gets P4, A3, P2 there is no conflict, but should we fix that and go ahead, right? So let's try to do that. That is, we'll fix, let's say A1 gets assigned to P1, A3 there is no conflict, A4 gets assigned to P4, right? If we do this, fine. Okay, so maybe I just give me some this thing to modify the instance so that it. So I have still not deviated from the bipartite graph that I have drawn because the top choices remain the same, right? So if I do this, then what, I mean all these posts are somehow gone, right? They are not available for me. So I should look at other posts that are there, remaining posts, and I would like to ask, is there a matching that is, can I get a matching which is popular by matching the remaining applicants to the remaining posts. It also is conceivable that I may have to leave some applicants unmatched because we have seen that their popular matchings may leave applicants unmatched. So there is nothing wrong in leaving them unmatched, right? But let us say that the preference lists of the applicants look like this, that is A1 has a post P5 which is some post, and A2 have A2, A4, so I should not use P2, P3. So A2, A4 and A5, all of them have their second choice as P3, right? So then these are the only remaining posts, P5, P3, P5 and P3, right? That those are the remaining posts among these applicants. So let's do the following, that is I will add this edge A1 P5, but remember A1 P5 is not interesting to me because I have already assigned A1 to P1, right? So there is no need for me to add this edge, but I will add these edges P3, right? These are the edges that I will add. And maybe I will also have yeah, so instead of this having A, I will also have this as P6. So sorry for changing the instance, but I will have this as P6. So again, it doesn't change the graph that I have drawn because A4 is again not in picture since I have fixed that, right? So now I will want to ask, can I get a popular matching by just extending this matching. So I have an initial matching A1 P1, A2 is not assigned, A3 P2, A4 P4. The only possibility is A2 and A5 can get assigned to P3, one of them, right, because capacities are 1. So the only choice that I have is A2 can get matched to P3 or A5 can get matched to P3, right? Yeah. Yeah, just hold on. So I just want to finish this. So I will say that if I assign A2 to P3, then A5 is left unmatched, right? Now, is this a candidate for a popular matching? So to show, we have never shown yet that a matching is popular except for one case where that was a trivial example. We haven't shown that some non-trivial example is a matching is a popular matching, but it is fairly easy to show that something is not popular by exhibiting a more popular matching. So is this matching a popular matching? So suppose I do the following, that is I will use another color to show. So let's say that I assign, so remember A5 is unmatched with respect to this matching. So if I promote A5 to P3, then I should, if I want to promote this, I cannot assign both A5 and A2 to P3. Therefore, I should take A2 and do something with it. I can leave it unmatched, but if I leave it unmatched, it doesn't give me anything. I get 1 vote, I lose 1 vote, right? But if I want to do the game that I did earlier of 2 promotions versus 1 demotion, is there a chance? I can do further promotions, that is I can actually promote A2 to P1, and then I still am not done because P1 cannot get 2 edges. Therefore, what should I do with A1? I can leave it unmatched because now I have gained 2 votes. I can afford to lose 1 vote, right? So this matching is not a popular matching because I can play this game of the rest of the applicants remain matched to the same edges, that is A4 is matched to P4, A3 is matched to P2, but I get 2 votes for the yellow matching versus I lose 1 vote. The yellow matching should be clear, these edges are changed, the A1 is unmatched, right? So that is the yellow matching, and I get 2 and lose 2. A similar thing will happen even if I try to match A5 to P3, and so remember the state we were in is that A2 and A5 had this only one post which is P3, and I wanted to match one of them, right? And because there is only one post, I would not be able to give 2 of them. Yeah, so now you had some suggestion. I will just erase this thing that I had done. So what this says is this matching is not popular. It doesn't say anything about the instance not admitting a popular matching. I lost everything. Yeah, but you wanted to suggest some other matching anyway, so great. So I will go with whatever is your suggestion. Yeah. Yeah, so what is your suggestion? Okay. Okay, A1 with P5, A2 with P1, A3 with P2, okay, because there is no conflict here, okay, okay, A5 with P3. Sorry, P5. Sorry, not P5. Yeah, it is P5, right? Yeah, okay. So now only A1 gets its second preference. A1 and A5, right. But as I said earlier that it is not as easy as characterizing it in terms of the second preference and so on. Uh, Actually, I could have done something more. I mean, these P5 and P3 need not have appeared at their second choice. You can think of lot of dummy applicants introduced with lot of their, each having their unique rank 1 post, and I could have shifted all of this down. So there is nothing to do with rank 1, rank 2, I mean not necessarily to do with rank 2 and so on. But you are right. So now this matching is indeed popular and we would like to see why it is popular, right. So one way is to try out all possible matchings and verify it by brute force that it is indeed popular. But you cannot expect this to be done with a large instance. Even with this 5 size instance, it is very difficult for us to do it. So what we want is, and how did she choose A1 to be matched to P5 and not something else? Is there another popular matching that I can get? And why is this popular is also not clear. So what we would like to get is a way to characterize a popular matchings, and therefore as a side this thing get an algorithm which gives us a popular matching, and if our algorithm comes to some condition, we will be able to say that there indeed does not exist a popular matching, right. So this is what we would like to say. So what we are going to do is write some or make some observations about the way popular matchings look like if they exist, because now we know that they may not exist, but if they exist then we will like to make some observations about how do they look like structurally. So these are some structural properties which will help us design an algorithm for computing a popular matching. So let's, like we have seen, we seem to be interested on focusing on the top choice posts. That is, initially as many as possible should get matched to their top choice. Is this true? That is, should every post which is ranked as a top choice post, should it be matched, or can some popular matching leave it unmatched? So we will call such post as, so we will call a post is called an F post, a post P is called an F post. So F stands for first post if some applicant ranks it as its F post, ranks it as its rank 1 post. So it's a very clear definition. So I'll call P1 as an F post, P2 as an F post, P4 as an F post, but P3, P6, P5 are not F posts because nobody treats them as their rank 1 post. So there's also a, so if I have a post which is an F post, then I can define this set F of P which is equal to the set of applicants that treat it as its F post, right. So let's write the set of FP1. What is FP1? Yeah, what is FP1? It is the set of applicants who treat P1 as their rank 1 post. A1, A2, right. So A1, A2 is this set, right. So this is some notation. So let's first ask, if I have a popular matching, can a popular matching leave an F post unmatched? That is, it is not assigned to anybody. It seems very unreasonable thing to do, because there are people who want it as its first post. Then why should you not give it, right? But this kind of intuition sometimes fails us. So we should write a proper proof that every popular matching must match an F post. This is what is the claim that we would like to prove. So we would like to show that every, or we'll just say that if M is popular, then every F post is matched in M. Okay, so if you want to prove this statement, how will you prove it? Yeah, so if you want to show some statement about a popular matching, you assume that that statement is not true. And if that statement is not true, your only handle is to show that if that statement is not true, you can construct a more popular matching than that, right? And this is fairly easy to do. Rather than showing that a matching is popular, showing that there is a more popular matching is fairly easy to do. So what she suggests is that if P is unmatched in M, then, and of course P is an F post, P is an F post which is unmatched in M, then let A belong to M of P, sorry, A belong to F of P, because there are some set of applicants who treat P as its F post. Then ask what is your matched partner in M. It may, that A may or may not be matched, we don't care, but A is clearly not matched to its F post. Why is it not matched to its F post? Because its only F post is P and that is unmatched, therefore it cannot be matched to its F post. So it can be matched to its rank 2, rank 3 or left unmatched. Wherever it is, just promote it to its F post. You will get another matching where all other applicants are indifferent between these two matchings, but this applicant A prefers the new matching M prime over this matching M. So what we formally do is M prime is equal to M minus A M of A, assuming A is matched, and union A union A P, right? So if I add this edge to M after removing A M of A, then I know that the matching that I get, we know that M prime is more popular than M, therefore it violates the assumption that M is popular. So if there is a popular matching, it must match every F post. In fact, you can say that it must match every F post to an applicant who treats it as its rank 1 post. Again, it seems intuitive that there's no incentive for us to assign it to an applicant who does not treat it as its rank 1 post. But how will you formally state this? So this shows that every F post should be matched. But what I am claiming is more, that is every F post should be matched to an applicant who treats it as its rank 1 post or belongs to FP, right? So if this statement is not true, that is, there is a popular matching, it matches every F post, but it does not match that F post to some applicant who treats it as its rank 1, then whom does it match to? It is, of course, it is not unmatched. So it is matched to somebody outside its F of P, right? So so this post P is matched, but it is matched to somebody who treats it as a rank 2 or higher, right? At least 2 rank, right? So it is matched to this applicant. This is A1. Now if I try to, so I know that there is another A2 which also treats it as a rank 1 because this is a F post. I can certainly try this trick of A2 getting matched to P and A1 getting unmatched, but that does not help me because I lose 1 vote and I gain 1 vote. So that does not help me. So recall again, our goal is to show that I have a matching which looks like this, that is it has a F post, that is it is somebody's top choice post, but a popular matching has assigned it to an applicant who treats it as its rank 2 or higher. And we want to contradict this, that is if we want to contradict this, we want to come up with a matching which is more popular than this. So again, every time you want to do this, you should think of, are there 2 people whom you can promote at the cost of 1 person whom you can let go down, right? So that we have 1 person, we know that A2 is our is the one which we want to promote. Is there some other person? Yes. Yeah. So who are the people whom you can typically promote? Hold on. Hold. See, unmatched rank 1 post is true, but now we know by the first claim that there cannot be a post which is called an F post and that is unmatched, right? So it is every F post, if you look at it, it is matched to somebody. But we want to show that it is also matched to somebody who treats it as its rank 1 post. But what I am asking is that, okay, so without worrying about getting more votes and so on, which are the applicants, if I am giving you a matching, which are the applicants that you can think of promoting? Not assigned to its F post. Is there an applicant who is not assigned to its F post in this picture? A1 for sure. Any other? A2's first choice is? No, yeah, A1 as well as A2, right? So A1 and A2 are both the applicants who are not assigned to their first choice. But what do we know? We know that if we try to promote A1, we don't know where A1's first choice is. Let's ask where A1's first choice is. A1's first choice is possibly P1. That must be matched to somebody. That may be matched to A3. But we don't care, because as long as we have got a handle of 2 people, that is A1 and A2, both whom we can promote. So we will now promote A1 to P1. First, actually we should say it in the other way, we will demote A3, that is we will delete this age A3 P1 from the matching. We will demote A3, then P1 becomes free, then A1 will get promoted to P1. Now P becomes free, therefore A2 will get promoted to P. So we have another matching in which there are 2 applicants who get who get promoted versus one that gets demoted. It has nothing to do with whether it was rank 2, rank 3 and so on, because there is a rank 1 which is available. Available, not free, but you can make it free, right? Yeah. Why? Why can't we demote it? So let's do that promotion. So let's draw it explicitly. So we will have a yellow matching in which we have A1, A2, A3. So A1 will get matched to P1, A2 will get matched to P, and A3 is actually demoted, so I will not match it, okay. Yeah. So now, so let's do the votes in between these two, because remember for the rest of the matching, the applicants are indifferent. There can be several other edges which are there in the matching, but those are as it is. They are the same in M and N, if I call the other matching N. So they just carry forward here. So whatever the applicants are there, A4 to AN, they are indifferent between these two matchings. So this is M and this is N. Now let's do the voting. Therefore, we can restrict our attention to only these three applicants. So how do the applicants vote? Where does A1's vote go to? This is P1 and P1 is its rank 1 post. So where does its vote go to? This P is greater than or equal to rank 2. So it goes to N. So it goes here. What about A2? It was unmatched versus it is here, or it may not be unmatched, it may have been matched to somebody, but it doesn't care, it is getting promoted. And A3 was matched and it gets unmatched. So from 1 it has got demoted to a long way, but it gives its vote here, but doesn't matter. It is a matching which is more popular than this, right? So therefore, we have played again the same trick, and in the rest of the proofs also you will see a similar trick being played, but you should be able to get the handle on which applicants to choose to get the more popular matching, right? Okay, so what have we established using these two? That if you look at the set of F posts, so I will go back to that example. So all these posts P1, P2, P4, they are very heavily demanded, or they are important posts, and they should be matched. They should be matched to participants who treat them as their rank 1 posts, right? We did that actually in the first matching, but the claim doesn't say anything about whom should it get matched to, right? And we can make mistakes if we arbitrarily fix somebody, right? Okay, is this fine? So what this tells us is that, okay, so I'll again, yeah, so it says that should be matched in M. Moreover, so M of P belongs to, every F post P is matching, M of P belongs to F of P. What this statement says is that the matched partner of P is coming from one of the applicants who treat it as its rank 1 and nobody else, right? So without knowing whether a popular matching exists, what we are saying is, if a popular matching exists, it must look like this. So if in this previous instance, if somebody gives you a matching in which A2 is matched to, if so there is nobody who is, so let me add something. So maybe I'll just add here P3, P2, P4, P1. So if there is a matching in which, if somebody gives you a matching in which A4 P1 is matched, then you should immediately say that such a matching cannot be popular and discard that matching from from being under consideration for being a popular matching. Is this clear? Okay. So we still have some more work to do to say how does a popular matching completely look like. So this is the first claim. So now if you look at the preference list, so this is an abstract instance A1 to AN, and there are these F posts, some P1, P2. I don't know whether the F posts are unique and so on, but there are some F posts. So what we are saying is that these F posts have to be matched, and they have to be matched to somebody who treats it as a rank 1. We do not know whom to assign them to, but you can think of them as being matched to somebody, right? So if there are some remaining posts, I mean if there are not enough posts to be matched amongst the F posts, there are some applicants who need some other posts, right? Then everybody need not get matched to their first post in a popular matching, but there may be some other posts may be of use. But if there are some other posts, there must be other posts which are left over after F posts have been removed. So what we can think of is, take the instance and remove the F posts from everybody's preference list. That is, even if a post, so let's say P1 is an F post, P1 appears as a third choice in A3's preference list, it doesn't play any role, because this A3 P1 edge is never going to get used in any popular matching. This is what the theorem states. So therefore it says that you can think of the graph being reduced. That is, you of course are interested in using these first choice edges, and we have not fixed the matching, but you are free to delete these edges. That is, A3 P1 is no longer playing any role. It can as well be discarded. So we can think of a reduced instance. Good. So yeah, so I don't think you should keep copying the instances, because I do keep changing, I'm sorry. Okay. So if this is my instance, I know that I should add these edges A1, P1, A2, P2, A3, P2, A4, P2, A5, P3, right? These are interesting edges. I do not know which amongst this is going to get matched, but these are interesting edges. Similarly, there are some edges which are uninteresting or irrelevant for me. And what are those edges? For example, this edge, A1, P2. So I will just say that this is a discarded edge, A1, P2, because this post is a rank 1 post, and I am never going to match it to somebody who doesn't treat as a rank 1. Similarly, A2, P3 is a discarded edge. A4, P1 is a discarded edge. And A5, P2 is a discarded edge, right? So now I have some reduced instance. F posts are anyway, I have added those edges to their rank 1. I have also discarded some edges based on the fact that these edges are never going to get used. That I have proved. So I have not done something wrong. So now where should I look for some remaining edges to be added? So, because as you can see, A1 gets happily its first choice, but A2, A3, A4 do not have posts to be added, I mean do not have enough to be matched. So, they need some more posts. Yeah, so what edges should I add for applicants? Okay, A1 P3. Okay, thank you. Yeah, yeah. So that is also a discarded edge. Yeah, good. Yeah, and anyway, in this example, A1 doesn't need anything. But yeah, that's correct. I'm never going to use that edge. But what do you think after the instance has been processed to some extent? Where should I, for example, A2 needs something more. Does it have anything? No, the only edge which was A2 P3, we cannot use it. What about A3? A3 does have P4, right? So it is possible. Let me just add one more P5 here. A3 has P4 as well as P5. Which do you think it should add an edge to? Again, it seems intuitive that it should add an edge to P4 rather than P5. When there is something better available, we add it to that. So again, we will try to add that and see whether we can formalize this. So let me add this edge A3 P4 and A4 P5, right? So what I will call this is that, so what I have done is for every applicant I have selected its F post and added edges to that. That was my first step. Then based on whatever are F posts which are appearing in the preference list of some applicants as non-F posts, like P2 was appearing in A1's preference list as a non-F post, I deleted that edge or discarded that preference. And now amongst the remaining posts, whatever remains, I am asking what is the most preferred post that you have, right? So the most preferred post that you have, I am asking and I am adding that as my second choice, the next choice. So I am constructing a graph which is a very small graph as compared to the original graph. The original graph has many edges. I am constructing a graph in which every applicant has at most two edges. One coming from its F post, the second coming from another post which if it is available, because for example A1 there was nothing else to add, A2 there was nothing else to add. So we will call this as the S post. It is called a second post of an applicant, and the S post of an applicant need not be its rank 2 post, but it is the most preferred post which is a post which is a non-F post in its preference list. For example, I will just add P3 here to make this look different. So if there was P3, then this edge is a discarded edge. So the rank of P4 in A3's preference list is indeed 3, but it is called its S post. So an S post of an applicant is the most preferred non-F post in its list. So I hope it is clear what it means non-F posts. So F posts are posts which are called as are rank 1 post for any applicant, and we have done a pre-processing of the preference list. That is, we have deleted all the edges or deleted or think of marking edges marking posts which are F posts for somebody. Of course, you are not going to mark you are not going to delete something which is your own F post, because that is your F post, but if any post which is ranked as an F post which appears in your preference list at other rank, you delete it, right? You think of that edge being deleted, and then whatever remains you will call it as your S post. Whatever is the most preferred post, you will call it as an S post. Is this definition clear? Yeah. so we have just listed out, so list out all the F posts. So in this example, P1, P2 and P3 are F posts. Is this clear? So go to every applicant's list. Of course, do not touch its F post, and then ask, is P1 appearing in your preference list as a rank 2, rank 3, anything? Wherever it appears, just delete it. Delete or think of it as being marked as not available for you. Right? Remember that if P1 is your F post, it cannot be your rank 3 or rank 2 and so on. So your own F post will not appear at a lower rank, but somebody else's F post can appear at a lower rank. Is this clear? Okay, any other question about? Okay, so will an S post always exist? No, right? This example itself shows. For example, A1 doesn't have an S post. A2 doesn't have an S post. A3 does have. A4 has an S post. A5 doesn't have, right? So we would like this S post to exist, right? We would like this to exist. So what we are going to do is, we are going to do a small pre-processing of the instance. That is, as soon as we are presented with the instance, we will say that I will add a unique last resort post for every applicant. So LA1, LA2, LA3, LA4, LA5. These are all dummy posts, right? Think of them as just being there as placeholders. So we will see that their addition is not going to change the answer to the question, does this instance admit a popular matching or not? It will not change the answer to this question. Whether they were present or they were not present, the answer will remain the same. But it will make some of the things easier for us. So what have we done? We have added a unique last resort post for every applicant. That is a dummy post. Think of it as a dummy post. Now when I scan this list, when I am deleting these F posts or unnecessary edges, this post will never get deleted, right? Because this is not an F post for anybody, so this will be untouched. So if nothing is there in your preference list which is a true post for you, then your dummy last resort post certainly qualifies to be an S post, because that is the post which is the most preferred post, which is a non-F post. So therefore now S post always exists from now on. So F post certainly is there for every applicant, because we know that preferences better be at least having one post, otherwise the applicant doesn't want to participate. So therefore F posts exist. Now by this pre-processing, S posts also exists, right? Okay, good. So now so S post may not come into picture always, because as we see, A3 doesn't even care about its last resort post. The last resort post need not come into picture. For example, A3's S post is its true post, which is P4. A4's S post is P5, but A5's S post is L of A5, right? So now S posts exist, and for some applicants they may be the last resorts. For some applicants, they may be true posts that were there in their preferences, right? Okay, good. So now what people observed, and this is a very nice result, and the whole thing that I am presenting is from a paper in 2005 by several authors, which include Abraham et al. And we will share the paper as well as the paper with you, so that you can read it. So they observed a very nice thing, that is, now you construct this graph where every applicant has only two types of edges. One, its F post edges, which we have already drawn, and its S post edges. That is, every applicant adds an edge to its S post. So let's do that. So here we have added, but we have some more edges to add. That is, A1 can get assigned to L of A1. A2 also has L of A2. A3 already has P4, A4 already has P5, A5 has L of A5, right. So this is what we have. Now this is a graph, very simple graph. It has, every applicant has 2 edges, so the graph has 2n edges, right. It has exactly 2n edges. And now if this graph admits a matching in which every applicant is matched, if every applicant has a post to be assigned to, then that matching is going to be popular, right. That is, if you can find a matching in which you can get a post for every applicant in this graph, in this reduced graph, then that matching is going to be popular, right. So this is what we will like to show. But before we show this, let's see whether we understand this. So so now in this graph, do we have a matching which matches everybody to either its F post or to its S post, because that is what the edges we have drawn. So is there a matching that we can find? So a matching is just again a collection of edges, yeah. So can we find a matching in which every applicant gets matched? Yeah. Do you have some suggestion? Yeah, so I don't know your name. Second row behind you. Yeah, behind you. Yeah. A1, P1, LA2, okay. A3 to P2, P5, A5 to P3. So very nicely what you have chosen is that whenever there was a choice between a true post and a last resort, you very nicely chose the true post. Did you do this consciously or it happened? Did conscious? Okay. Okay, but if that was your intent, maybe you could have also done A3 to P4 and A2 to P2, right? So if that was your intent, you could have matched A3 to P4 and A2 to P2, right? That would have avoided even the LA2, right? But what is good about this is that even when the algorithm had a, or even when her matching algorithm in her mind had a choice to match A1 to L of A1 versus P1, she did choose A1 P1, and that must be chosen because we know that every F post must be matched. If one chooses a matching which is A1 to L of A1, then that matching cannot remain popular because that will leave P1 unmatched, right? So it is a good thing. Here it does not affect, as we will see, it will not affect the case that it is popular or not. In fact, we should do this exercise. So let us write this matching A1 P1, A2 L of A2, A3 P2, A4 P5 and A5 L of A5, right? Sorry, no, not L of A5, A5 P3, right? This is one matching, and what I will say is, I will just not write A1 P1 remains matched the same way, A2 gets matched to P2, A3 gets matched to P4, A4 gets matched to P5 and A5 gets matched to P3. Let us see how do these matchings compare in terms of their popularity, right? So A1, A4 and A5 do not vote because they anyway are getting the same partners. What about A2? So I will call them M and N. What is vote of A2? N. So A2 votes here, right? What about A3? M, right? So now these votes have got compensated. This doesn't prove that any of them is popular we will show that these are popular, but certainly one of them is not beating the other. But one more thing we should observe is, what is the true size of this matching M? I mean, how many edges are there truly in this matching M? 4, because A2, L of A2 is really a dummy edge. We are just doing it for the sake of our convenience. That's not a true edge. So whenever you match an applicant to its L of L post or last resort post, that is a dummy edge that you have matched, or that is a dummy match, and therefore you should not treat it as a true match. But what we will show is both these matchings are popular, and therefore it shows that in fact popular matchings come in different sizes. They can be of different size, and they indeed they can be different sized matchings. This matching is truly of size 5, this matching is of size 4 only, right. So this is what this example illustrates. Is this fine? Yeah. Yeah, so we will see that, so as I said, I have not given an algorithm. We will see that our algorithm it must match every F post. Therefore, as a consequence, it will try to have fewer people matched to their S posts. But leaving somebody unmatched versus having more number of people matched doesn't affect the popularity, is what, if you for now believe that these two matchings are popular, this illustrates. Okay, so what we have just defined is F post and S post. We will write the theorem and maybe prove some things, and then, okay, so what we know is that if M is popular, then every F post P is matched to an A belonging to F of P. Now we will make the second claim, that is, if M is popular, every applicant is matched to either its FA or SA. So I hope this notation is clear. F of an applicant, F of A is its rank 1 post, S of A is its most preferred post, which is a non-F post, right. And whether a true S post is there or not, we do not care. It may be its dummy last resort post. So we want to show this. That is, if M is popular, every applicant is matched to either its FA or SA, right. So let's look at an applicant's preference list. Its FA is its true top choice. There may be several posts here. There is SA, then there is something here possibly. This SA could be its last resort. If I take any arbitrary post here P, what can I say about P? What is there a property about P that I can say? It must be an F post. Some other applicant must be treating it P as its rank 1 post, right? Otherwise, this post would have been my S post. Applicant A's S post. Good. So now what we will try to argue is that, so if M is popular, okay, so if M is popular, M of A is not equal to P. What do I mean by P? A post which is strictly nested between its F post and S post. This cannot happen. This is what I want to show, right. So what this claim says is that every applicant is matched to either its FA or SA. So if it is matched to its FA or SA, I am done. So, the only possibilities are it is between FA and SA, or it is strictly worse than SA, right. There can be things like in our example, this P5 is strictly worse than S of A3. So, we would like to show that a popular matching cannot match it to that. So, yeah, so if M is popular, then M of A cannot be equal to P. First we will argue that it cannot be strictly nested between F of A and S of A. So again we will ask, what happens if it is nested between its F of A and S of A? We just want to play the game, right? We are now used to it. So please use that and come up with an argument where you say that if you have such a matching, I will show you a more popular matching. Yeah, you had some argument. I would like everybody to participate. So yeah, again I would like to draw the picture. A is matched to P in this claimed popular matching. We know that this is neither its F post nor its S post. So its F post is somewhere better, F of A, and there is something more which you know by now, which you should use to get 2 promotions. Yeah, you want to try? Yeah, the penultimate row. Yeah, yeah. So at least please let us know, is there one applicant that you can promote? You understand what is promotions? Okay, somebody else wants to help her. Yeah, there may be somebody who is matched here. You have to demote that person. So let's call it A prime, okay? So good. So we know that there is some other applicant which is A double prime who treats P as its rank 1 post, right? And that applicant is not matched to P because P is matched to A. Therefore, we can promote A to P, A double prime to P, A to F of A, and demote the applicant A prime to be unmatched, right? In which case we get 2 promotions at the cost of 1 demotion. And therefore, we have argued that it cannot lie in this between F of A and S of A. A very similar argument will let you do that it is not strictly less than S of A. I will leave that as a small exercise. It is a very similar proof. So I think we will stop here. We will complete the argument and we will show the algorithm what it does, but it is almost immediate now that we will draw this, we will construct this reduced graph and compute a maximum matching in this graph and do some adjustments to make sure that all F posts are matched.